Testing. All right, Math 0092. Sorry about that. 0092, we're going to start Chapter 10. Chapter 10, we're introducing real numbers. I just wanted to take a look at this chart that's given to us. It's on page 599. In 1972, the western Indian manatee was placed on the U.S. endangered species list. A large percentage of the number of annual deaths of this species is due to human factors, such as collision with watercraft, as illustrated in the accompanying graph. Since 1972, concerted efforts by conservationists have led to a great enough increase in the number of manatees that the species may be reclassified as threatened instead of endangered. The Florida manatee mortalities for 2016, and we have a pie chart. It's segmented into different wedges representing different percentages. For the dark blue is deaths undetermined, which is 28.7%. Perinatal is the red for 21.7%. Watercraft deaths, kind of this blue, light blue color, 20.0%, and so on. And we want to be able to read numbers that now have decimal points, percentages, accuracy to 3 or 4 places following a decimal point. And that begins to take us into the real number system. So we are going to be introducing the real numbers, and I just want to review a bit with you. Our whole numbers, remember the whole numbers we think about, well, there's a whole, so 0 is our big whole, and then we have our counting numbers, and we continue in that fashion. We then introduce the integers. And the set of integers is so we have our whole numbers right here. The counting numbers, which is right here, 1, 2, 3, 4, 5. And their additive inverses. So we have the whole number, 0, the counting numbers 1, 2, 3, 4, 5, 6, and their additive inverses, -1, -2, -3. And remember the additive inverse is the opposite. The opposite of 1 is -1, the opposite of 2 is -2, and the opposite of -3 is +3. We just wanted to remind ourselves that 0 carries no sign. So 0 is neither positive nor negative. We then introduce the rational numbers. The set of rational numbers. Rational numbers can be described as the set of A over B, where A and B are integers. So they can be from our integer set, except B cannot be equal to 0. B's position is in the denominator location, and we cannot allow division by 0. Division by 0 is undefined. And we want to remember that. That's something to memorize. Division by 0 is undefined. So we could talk about numbers like 1/2. Well, A's position in the numerator is an integer and B's position in the denominator is an integer. So we have A over B where both are integers and we're not dividing by 0. So that would be a rational number. 1.5. Let's see, 1.5 is, well, let's look at our number line here. 1.5 would be right about here. 1.5 about 1.5. And 1.5, we can recognize that as 3/2. And 3 is an integer, 2 is an integer, and neither are equal to 0 in the denominator. So a rational number in decimal format. Well, to further define rational numbers in decimal format either terminate or repeat. So sometimes in order to determine if a number is a rational number, we'll have to convert to decimal format to see if it either terminates or repeats. So let's look at 1/2. Well, 1/2 in decimal format, you can look at our calculator. 1 divided by 2 is 0.50. And as a decimal equivalent, it either terminates or repeats, and 0.5 terminates. It is 0.5. A -5/8. That's in fractional format. Looks like we have an integer divided by an integer. Well, let's see. A -5 divided by 8 in decimal format. Let's just make our number of places following the decimal point a bit more so we can be a little more accurate. You'll have to do that on your calculator. I have a -5 divided by 8. I get a -0.625, and then it seems to be terminating. It's not continuing. So -0.625. So it is a rational number. -5/8 is a negative rational number because in its equivalent decimal format, it is terminating. Let's see, it's 7/11. We have an integer divided by an integer where the denominator is not equal to 0. Let's check on our calculator again. 7 divided by 11. And I get 0.636363. That's an example of a repeating decimal. 0.63, and we put the bar over the placeholders that repeat. 0.636363. So it either terminates or repeats. So 7/11, yes, it is a rational number because in its decimal equivalent form, it repeats. Now how about 8? 8's just our counting number. And 8 is the same as 8/1, which is in our format A over B, where A and B are integers, and the denominator is not equal to 0. So in decimal equivalent form, 8 is 8.0, and it terminates. So yes, it is a rational number. And then we define irrational numbers. Now, irrational numbers, this "ir" out in front, "ir" as a prefix is equivalent to not. So irrational numbers are not rational numbers. And in their decimal format will neither terminate nor repeat. So if we're given the square root of 3 on your calculator, you'll need to determine how to solve for the square root. I'm on a TI-84, and I'm going to call for the second. It's a blue symbol, and it looks like a square root symbol. The second square root of 3, and I'm going to close with a parenthesis and then enter, is 1.7320, and it continues here, 508. And I've got pretty good accuracy following the decimal point, and it doesn't look like it is terminating. So it will neither terminate, doesn't look like it's terminating, and it doesn't look like it's going to repeat. So is it irrational? Yes, it is irrational. In decimal format, it will neither terminate nor repeat. So we had to convert to decimal format with our calculator and kind of expand the placeholders following the decimal point to investigate. How about a negative square root of 8? Well, again, negative the square root of 8, close, enter, and I get negative 2.8284271. I get negative 2.8284271. And to the best of my calculator's ability, it's neither terminating nor does it repeat. So yes, it is irrational. How about the square root of 25? The square root of 25, close with your parenthesis, is equal to 5.000. And that terminates. This is an integer, 5.0. 5 is a counting number. So it's a rational number, not an irrational number. And pi. Now you should find on your calculator the symbol pi. I have on my far side blue code calling pi, and then I get the symbol, enter, and I get 3.1415927. Now it doesn't look like this is terminating, and it certainly isn't repeating yet to the best of my calculator. So an irrational number neither terminates nor repeats. So it is irrational. Now, these are a few of the first examples that we've given, but the square root of 3 and pi are very good examples of irrational numbers that you will want to remember. But be that as it may, when you're given a number, testing to see if it's irrational or not, you'll need to convert that number to its equivalency in decimal format and investigate to a high precision following the decimal point. Does it terminate or repeat, or does it not terminate nor repeat, to determine if your given number is rational or irrational. A couple of tests that you have to practice so you can determine if a given number is rational or irrational. So then on page 604, we're looking at our real number system. There's a nice hierarchy chart on page 604. And we define the real numbers as the set of rational numbers and irrational numbers. And then we break down the rational numbers into the integers and the rational numbers that aren't integers, like our fractions, 2/3, -4/5, and 8.2, and so on. And we break down our integers into the positive integers, which would be 1, 2, 3, 4, our counting numbers, sometimes called the natural numbers, 0, and then the negative integers, -1, -2, -3, and so on. This is a very important page because you're asked to be able to determine if a number is a real number. Is it an irrational number? Is it a rational number? Is it an integer? Is it a whole number? Is it a counting number? And so on. So very important, page 604. Well, then we begin to work with our real numbers, and we want to be able to determine order. So we're checking to see if -7 compares to 3. Is -7 greater than or less than 3? And we can sketch that on our number line. 0, -7, +3. And we see that -7 is to the left of 3, our arrowhead here. -7 is to the left of 3, so -7 is less than 3. -18 compares to -15. We can sketch that on our number line. 0, -15, -18. We can see that -18 is to the left of -15, so -18 is less than -15. And 1.5 compares to a -2.7. 1.5, a -2.7, and 1.5. 1.5 is to the right of -2.7. 1.5 is to the right of 2.7. So 1.5 is greater than a -2.7, and actually any positive number would be greater than any negative number. Then you might be asked to compare 5/8 compares to 7/11. I'm going to use my calculator, and I have 5 divided by 8, and convert that. It's 0.625 compares to, and we're going to compare 7/11, and that's 0.636363. Repeating. So 0.625 is less than 0.63. 0.62 is less than 0.63. So 0.625 is less than 0.63. Again, comparing fractions, convert to their decimal equivalent, and then compare greater than or less than. Continuing with working with our real numbers, we want to introduce absolute value. Absolute value. We want to know the absolute value of 3. We use the absolute value bars. They're just vertical bars around your expression. The absolute value of 3 is absolutely, positively 3. It's 3 units from 0. The absolute value of -5. The absolute value of negative 5 is absolutely positively 5 units from 0. So you see, absolute value is not concerned about the sign or direction. Absolute value is concerned about absolutely positively the unit distance from 0. And distance we don't measure as negative. So its absolute value always returns a positive result, the unit distance from 0. So the absolute value of negative 10 is absolutely positively 10 units from 0. And the absolute value of negative 2.73 is absolutely positively 2.73 units from 0. Absolute value. You may be asked to graph on the number line. We're supposed to graph 10/3. Sketch your number line. One, two, three, four, five, 6. 10/3. Well, 3 goes into 10 3 times. 3 times 3 is 9. Subtract, we get a remainder of 1/3. So I want to go to 3 and 1, 2, 3. So I'm right about here for 10/3, which is equal to 3 and a little bit, 3 and 1/3. We're asked to graph a negative 5.2. One, two, three, four, five, 6. Here's negative 5, negative 4, negative 3, negative 2, and negative 1. Now negative 5 is right here, plus a little bit, right about there. Negative 5.2 on the number line. If we're given 5/6, I'm sorry. If we're given 5/6, what is its decimal equivalent? Well, we'll have to use our calculator. 5 divided by 6, and I get 0.83333, where 3 is my repeating digit. So 5/8 in fractional form with a numerator and a denominator is equal to, in decimal format, 0.83333, a repeating decimal. And then negative 3/8, convert that to its equivalent decimal format. Negative 3 divided by 8. Negative 3 divided by 8 is a negative 3.375. Negative 0.375, and it seems to terminate. Well, now that we have our real numbers defined and able to determine if we have a real number, a rational number, an irrational number, an integer, a whole number, a natural number, we're ready to begin to manipulate our real numbers under operations of addition and or subtraction. So we want to define on page 609 the rules for addition of real numbers. Now there's a set of about 4 plus some details on how to add real numbers, and you will want to memorize this. And we will work on examples to help put this into place for you. we will be trying to memorize how to add real numbers. So if I have 2 plus 3, 2 is positive, 3 is positive, so I have positive 5. If I have 7 plus a negative 2, I have 7 plus a negative 2. I need to subtract 2 from 7, get 5, but 7, the absolute value of 7, remember our absolute value? The absolute value of 7 is greater than the absolute value of 2, so my answer is positive. If I have negative 7 plus 2, I'm going to look at the absolute value of each number. That's 7 and 2. Subtract the smaller absolute value from the larger absolute value, that'd be 5, and keep the sign of the absolute value, which is larger, and 7 is greater than 2, so this is going to be a negative 5. Using your absolute value, that strips it of sign, of the negative sign, by the way. So we get 7 and 2, subtract the smaller absolute value from the larger absolute value, and I get 5. And then keep the sign of the absolute value that's larger, and the absolute value of 7 is larger than the absolute value of 2, and the sign is negative. So my answer is negative 5. I have a negative 12 plus a negative 7. If I have a negative number plus another negative number, my number remains negative, and 12 plus 7 is 19, but it's going to be negative. I just made negative 12 more negative by adding some more negative value to it, so my answer stays negative. A negative 1.4 plus 8.5. Well, then our directions say to take the absolute value of each number, which is their now the numbers are positive, and subtract the smaller absolute value from the larger absolute value. So I'm going to get 17.1. And I'm going to keep the sign of the absolute value that's larger. Well, 8.5 is larger than the absolute value of 1.4, so this is going to be a positive answer. So please practice your directions for adding signed numbers. Well, then 15 plus 0, 15 plus nothing would be 15. A negative 2 plus 0 is a negative 2. I didn't move it all on my number line. A negative 9.2 plus 3.1. Take the absolute value of each, so it strips it of its sign, subtract the smaller from the larger, and keep the sign of the absolute value that's larger. Well, the absolute value of 9.2 is greater than the absolute value of 3.1, so my answer is going to be negative 6.1. A negative 2/3 plus 5/8. Well, we remember that when we add or subtract fractions, we have to think about the piece of pie, and we need a least common denominator. My denominators are different, so I'm going to have to find a common denominator. So I'll build my least common denominator table. That's 1 times 3 and 2 times 2 times 2 with prime factorization. From the first column, I need a factor of 3. From the second column, I need a factor of 2, another factor of 2, and another factor of 2. So I have 8 times 3, which is 24. My common denominator is 24, so I'm going to convert each of these to 24ths. So a negative 2/3. 3 times what would give me 24? 8. 8 times 3 is 24, so I'll have to multiply the numerator by 8 as another name for 1. I'm not changing the value of my fraction. I'm just changing the way it looks as an equivalency in 24ths. Plus 5/8. 8 times 3 would be 24. If I multiply the denominator by 3, I'll have to multiply the numerator by 3 as another name for 1. 1 times any number is a number itself. I'm not changing the value of 5/8. I'm just changing what it looks like in 24ths as an equivalency. 8 times a negative 2 will be a negative 16 over 8 times 3 is 24, plus 5 times 3 is 15, and 8 times 3 is 24. So now I need to take the absolute value of each. So I'm just going to remove the sign. Absolute value removes the sign, and subtract the smaller from the larger, which is 1. And I keep the sign of the larger value and the larger absolute value, which is this case negative. So my answer is negative 1/24. Now there may be times that we're asked to add. And in this case, I have 15 plus a negative 2, and I'll protect that sign with parentheses, plus 7, plus 14, plus negative 5, and I'll protect the sign with parentheses, plus a negative 12, and I'll protect the sign with parentheses. 15 plus a negative 2 plus 7 plus 14 plus a negative 5 plus a negative 12. Well, this is all addition and or subtraction, so I can combine my positive terms, 15 plus 7 plus 14, and combine my negative terms. 15 plus 7 plus 14 is 36, and adding all my negative values, my answer is going to be negative, get negative 19. And now I'm adding 36 plus a negative 19, so I take the absolute value of each, remove the sign. Absolute value, we're looking at the positive value of the number. Subtract the smaller from the larger. 19 from 36 is 17. And then we keep the sign of the absolute value, which is larger. And 36 is larger than 19, so we're going to keep the positive sign. We're asked to add. And I have a negative 2.5 plus a negative 10 plus 6 plus a negative 7.5. And again, I can regroup these as a negative 2.5 plus a negative 10 plus a negative 7.5 plus 6. Adding my negative numbers, negative 2.5 plus a negative 10 plus a negative 7.5 is negative 20, plus my positive numbers, 6. Now I'm adding assigned numbers. So I take the absolute value of each, that'll be their positive value, subtract the smaller from the larger, and I'll get 14. And I keep the sign of the larger absolute value, and 20 is larger than 6, so it'll be a negative 14. Remember opposites. 34, its opposite is negative 34 because when we add opposites, the answer is 0. 34 plus a negative 34 is 0. If I have a negative 8, its opposite is 8. And if I have 7/8, a negative 7/8, its opposite is positive 7/8. 7/8 plus a negative 7/8 is 0. When I add opposites, the answer is 0. Something interesting is that the opposite of any real number is the real number itself. So if I have the opposite of negative 7, Here's -7, and I'm asking for its opposite. The opposite of -7. That's the opposite of -7. If I have -7, its opposite is +7. So sometimes we're asked to evaluate. We're supposed to evaluate -x and the opposite of -x. We're supposed to let x equal 16. Well, with -x given, I'll substitute 16 for every value of x, and I'll carefully copy everything down the same, but we're going to let x equal 16. So if x is 16, the opposite of x is -16. We're going to let x equal 16. I'm going to substitute into the opposite of x. So for every occurrence of x, I'm going to let x equal 16, but I'm going to copy everything else down the same. So I very carefully substitute 16 for x's position. Everything else is copied down the same. If I have -16, its opposite is +16. The opposite of -16 is +16. Let's try another one. Let x equal 3, or a -3. So I'm supposed to find -x. I'm going to copy everything down the same, but I'm going to substitute for every occurrence of x. This time x is -3, so I'm going to protect my sign. Now I have -3. The opposite is +3. The opposite of -3. The opposite of -3 is +3. And we're going to let x equal a -3. And I have the opposite of x. I'm very carefully substituting. I'm going to copy everything down the same, except for every occurrence of x, I'm going to substitute -3, and I'm carefully protecting the sign. So now I have -3. Its opposite would be +3, and the opposite of +3 is -3. I have the opposite of 3, -3. I have the opposite of -3, which would be +3, and the opposite of +3 is -3. You may want to spend some time evaluating those examples, and they're found on page 611 with some more examples for you to practice. All right, that takes us through section 10.1 and 10.3. We will be continuing in chapter 10 with additional recorded lectures. Please return to D2L for all your details regarding homework, assignments, tests, and due dates. And I'll be creating the homework at my math lab for chapter 10 soon. Thank you very much.